Hello world, and welcome to the kitchen series of gravitational waves. I'm Mihai, and I used to teach this to the gods. If you look at Kip Thorne's filmography, I did reality, and after me came Chris Nolan, who did fiction in Interstellar and history in Oppenheimer, but reality was mine. And I'm also responsible for the longest footage of Kip available on the internet worldwide. But now I will teach gravitational waves myself, which is a daunting task, and I'll probably fail. Now, if you do want to learn gravitational waves for real, go learn from the gods and use my lectures with Kip. When I was a kid, I used to have this rule that I don't waste my time on stupid people. And that meant that whenever I used a book, I wanted a Nobel Prize on the cover. Now, there's one thing that's better than a book with a Nobel Prize on the cover, which is a book where you put a Nobel Prize on the cover. And they made that exemption for Mr. Thorne and Wheeler, Gravitation. And then end up doing a bit of original work, which was part of the body of work that Kip's Nobel Prize was awarded for. And now that book has a Nobel Prize on the cover, so it's no longer failing my criteria. Okay, now back to our business. So we want to talk about gravitational waves. But first, we have to define the space-time, which is the medium that these waves are propagating through. So unlike sound waves, which are oscillations of air, gravitational waves are waves in the geometry of space-time itself. So basically, if a gravitational wave comes between you and me, the distance between us will change without us moving. But let's take a step back and go to special relativity, which is how we introduce the space-time. So, before Einstein, people used to measure time in seconds and space in meters. And there were two different things. Like, time was what you measured with your clock, and space was what you measured with your yardstick. And they wouldn't combine themselves. They wouldn't have sex with each other. Einstein's genius idea for special relativity was to say that these things, like measuring time in seconds and space in meters, sucks. So what Einstein wanted to do was measure both in the same thing. Now, when you measure time in meters and space in meters as well, then you're going to have a natural, very interesting speed, which is 1 meter of space in 1 meter of time. And that's the speed of light. So the fundamental thing in special relativity and general relativity, the first thing you do in a general relativity class, is that you set the speed of light to 1, which is 1 meter of space divided by 1 meter of time is 1. But there's still something special about time, because I can't really go in the past the same way as I go to the bathroom. So that's what makes. We should look at what makes time special. So if you think about space and time, and let's say this is time, and now this is space. Then you want to ask yourself, how do you write Pythagoras' theorem? So we have here a triangle where we have some length in time and some length in space. And now ask yourself, what is the length of the hypotenuse? Now, if this was space, then the hypotenuse will be the square of this plus the square of that under the square root. we call this, let's call this ds, let's call this dx, and let's call this dt. So ds squared equals to dx squared plus dt squared. Now, if the world was to be that way, I could go in the past as I go to the bathroom. And I could go to the future and I could go to the past and come right back. And there would be no time. Now, the other way you can write Pythagoras is with a minus, which is ds squared equals to dt squared minus dx squared. Or the other way around if you want. Now, if you write with a minus, you're going to have some interesting things. Which is, when you have something going at the speed of light, it will go 1 meter of time in 1 meter of space. So then, what would be the length of this? Well, it's going to be 1 minus 1 equals to 0. Which means that the length of the world line of an object moving at the speed of light is 0. Or it also tells you that if you go at the speed of light, you stop aging. And you may have heard this from science fiction movies. Well, that's why. Now, up to a change in reference frame, which is stretching and squeezing space and stretching and squeezing time, up to a change in reference frame, any metric of any spacetime can be written either like this or like that. Now, this is not our world. This does not have time. And this is the world we live in. So that is for you the essence of special relativity. Which is, if you take a reference frame, time, space, and now you're going to get a moving object which will go less than a meter of space in a meter of time. If you go less than a meter of space in a meter of time, it means you go slower than light. It will look something like this. And what you see is that the length of the world line of the moving observer will be less than the length of the world line of a stationary observer. Now, you'd want to ask yourself maybe what will be what the space of the moving observer will be like. And in accordance to this metric, in order to preserve orthogonality, the space of the moving observer will be something like this. So it may not look like this to you because you're used to Euclidean spaces, and with this metric here, where both dimensions are sort of the same and you have no time, but these two things are actually perpendicular. In the same way as these two things are perpendicular here. And as you move towards the speed of light, this will be the world line of a particle moving at the speed of light. You will see that your space and time join together, and your whole reference frame sort of collapses. And moving past the speed of light means you have to go past the point where your space and time become the same, and you stop aging, and all those strange things happen. And this is partly why, or maybe this is how you can see why going faster than light is a problem. Now, a different problem is that if you can manage to go faster than light, you can also go in the past, and you can also do a lot of other things, and get stuff with negative mass and negative energy and all that stuff. But okay, now we've understood that space and time are both measured in meters. We've seen that there is a special speed where you go 1 meter of space in 1 meter of time, which is what we call the speed of light. Now, I leave it to you as a homework, and you'll get a Nobel Prize if you solve this homework. I leave it to you as a homework to prove that perhaps nothing can move at any other speed than light. Like you see, this observer here, which moves at, say, a meter of space in 10 meters of time, would be 10% the speed of light. I have a gut feeling that as a fundamental particle it can't really exist. And the way God makes stationary particles is that it sends one of these photons in a compact direction. So our world has a few extra dimensions which are compact. Your stationary particles are simply light that goes around the compact direction. And then it would be seen as stationary in the non-compact dimensions. You can sort of see it because, say, if you have an electron and a positron come together, they make light. Each particle is an antiparticle, and when the particle and the antiparticle meet, they make light. And also, in some not so special circumstances, it's possible to have the reverse process, which is when you have two light particles come and meet and form a pair of electron positrons, for example. And I think the way light forms particle-antiparticle pairs is that it gets deflected in these extra dimensions. But enough speculation, and I hope you get your Nobel Prize for that later. Okay, now how do we get to gravitational waves? So special relativity unifies space and time. And now, but in special relativity, the space and time is like a fixed arena, which is like a mathematical construct, which doesn't have much dynamic or much use or much, it's just a model. And why should it be that way? Why should it be rigid? Why should it be fixed? And it doesn't have to be fixed, it doesn't have to be rigid. And in fact, the space-time, so this arena in which we live, is something that can vibrate. And that's what Einstein did with his general theory of relativity. He allowed the space-time geometry to change. He allowed the space-time to vibrate. He allowed time to go in different directions in different places in space.